Welcome to the first presentation in Unit 3 entitled Red Bull Gives You Nothing Special. It says haters never win. I think that's true about life because negative energy always costs you in the end. Tom Hiddleston. So, students will be able to identify different types of energy and evaluate different sources of energy commonly used. So, what we already know the sun provides energy to the earth in the form of light and heat. There are advantages and disadvantages to different types of energy, and that the energy you get is conserved. The energy you get has to come from somewhere. And we know that's the law of conservation of energy, that we're going to abbreviate as LOCE, Law of Conservation of Energy. Okay, what we learned in the lab is that energy used comes from calories of food. There's a difference between a capital C calorie, which is referred to as a dietary calorie, and there's something called a small c calorie, which is a scientific calorie. And there's a difference between the two. A dietary calorie remembers the same thing as a kilocalorie. And that caffeine does not give you energy. What it does is it allows you to speed up the access of that energy. So energy exists in many different forms and it's always conserved in a system. You can convert one type of energy to another, like heat into light, like you do whenever you have a fire. Heat, you use it to burn the wood. The wood then generates a lot of heat, which ends up glowing and it produces light. This right here is something that measures electricity usage at your house. So, how much energy do you use every month? And then you're billed accordingly. Common types of energy are chemical potential energy. Chemical potential energy is the energy that's stored in a chemical bond. So, something like a carbon bonding to a hydrogen, this is stored energy. You have the gravitational potential energy, which is this energy stored due to an object's position relative to Earth. So if you have an object and that object is on the Earth, it has zero potential energy. But if you raise that object above the surface of the Earth, it has the potential to fall. Because it has the potential to fall, it has gravitational potential energy. Next, you have nuclear energy. Nuclear energy is the combination or splitting of nuclei. So if you take two nuclei and slam them together, and create a larger nuclei, that's an example of a nuclear reaction. You have radiant energy, which is energy transmitted by electromagnetic waves. So that's things like light and X rays and things like that. You have heat, which is sometimes referred to as thermal energy, which is the transfer of energy by objects at different temperature. So if you have something that's 100 degrees and you touch it to something that's 0 degrees, the energy will flow from one side to the other, and we call that energy flow heat. In addition to that, you have kinetic energy, which is the energy of movement. So anytime something moves, it has kinetic energy. You have work, which is considered to be the action energy that is related to force. And then you have elastic energy, which is the potential due to a stretch or a compression, like you see here with rubber bands. So, describe the transfer of energy from the sun to the sugar in plants. Well, if you start at the sun, you can start in the middle of the sun and say the sun's energy is a nuclear reaction. That nuclear reaction produces light. That light comes to the earth. That light is then transferred into the sugar in plants via photosynthesis, which is called chemical potential energy. Next, you have described the transfer of energy as a box is picked up off the ground and set on the table. So the first thing you have is you have an object that is picked up. So it's the action energy. You're actually taking an object and you're picking it up. So that's what we call work. Whenever you pick it up off the ground, that work then is transferred into gravitational potential energy, or GPE for short. Next, it says describe the energy transfer as a car initially moving down the highway slams on its brakes. So we have a car that's moving. Because it's moving, it initially has kinetic energy. Now, whenever it slams on its brakes, that energy has to go somewhere. And that energy actually goes into the form of what we call heat or thermal energy. If you were to touch your brake pad whenever you've slammed on the brakes, it gets very, very hot very quickly. So, energy usage. You can use energy every day as you exercise, walk, breathe, digest. Even thinking requires a minuscule amount of energy. So, all these things require some sort of energy usage. So, we use food as our fuel. You must consume energy for your body to properly function. Okay, your energy comes from the form of calories that you see on nutritional labels. Those calories your calorie requirements vary depending on your size and activity level. A lot of people say, well, it's 2000. Well, it's 2000 if you're a certain size and a certain activity level. But if you're smaller or if you're more active or less active, this number is going to change. Now, dietary calories are not the standard unit of measure. In addition to that, a dietary capital C calorie is really a kilocalorie. So when you look on the back of something and it says 100 calories, what that really means is 100,000 small c calories. Now, don't go thinking that, if I have this drink, it's this 100-calorie drink is going to be 5 times my daily requirement. That's not the case. You do need, if it's 2,000 kilocalories of energy per day. Now, it's just important to distinguish between what a dietary calorie is, which is really a kilocalorie, and an actual scientific calorie. A calorie is defined as the amount of energy required to raise 1 gram of water 1 degree Celsius. So if you have a small cube of water, okay, it's about 1 milliliter. It is 1 milliliter. In order to take 1 milliliter of water and raise it 1 degree, that's defined as a calorie. Now, nutritional labels actually use dietary calories, which, if you were to put it in perspective, would be 1 kilogram of water or 1 liter of water, which is much, much, much bigger. So 1 liter of water, 1 degree Celsius. Now, the standard unit of energy isn't the calorie or the kilocalorie, it's actually the joule. The joule is the SI equivalent, or the standard international unit, and 1 calorie is 4.184 joules. A lot of nutritional labels in Europe actually express things in kilojoules as opposed to kilocalories. And whenever they do put calories, if you'll notice, they do put kilocalories instead of just calories. So you see kilojoules and you see kilocalories. Now, one dietary calorie is 4.184 kilojoules. But really, this is the one we're interested in. We're not really interested in kilojoules all that much. So it says, what is the fundamental unit of measurement for energy? The fundamental unit of measure for energy is, well, first of all of these things measure energy, but the fundamental unit is the joule. It says a common dietary requirement is 2,000 calories. How many scientific calories would that be? So we're going to set this up using dimensional analysis because it's going to be a little bit easier. So we say 2,000 capital C calories. Draw our line, and we'd say 1 calorie is 1,000 small c calories. And because of that, we can go ahead and multiply it across, and you would end up getting 2 million small c calories. Next, it says how many joules of energy are in a 20-ounce Coke. So if you were to look at this, we have this is an 8-ounce Coke, and it's 1 can. It's an 8-ounce Coke. It's pretty small. Oh, it's 8 ounces on the nutritional label. So when you look at the nutritional label, it doesn't actually match up, which is interesting. So you have 8 ounces right here, and then it's 140 calories. Oh, no, this is a 12-ounce can. So you have a 12-ounce can, and that ends up being 140 calories. So you have 140. I'm going to change colors just because it's going to be easier. 140 capital C calories. Now those 140 calories are converted into regular calories. So 1 capital C calorie is 1,000 small c calories. Now this is per 12 ounces. Okay, the next thing we need to do is we've gone to calories, but we want to know joules. For every 1 calorie, there are 4.184 joules. So now, the last thing that we need to do is we actually need to take care of this ounces. It says in a 20-ounce Coke, so we multiply it by 20. So you have 140 times 1,000 times 4.184 times 20, and all of that's divided by 12. So at this point, we can set up our calculator, or we can plug it into our calculator. 140 times 1,000 times 4.184 times 20 divided by 12, and you end up getting something along the lines of about 975,000 joules of energy. So how many kilojoules of energy does a person consume a year on an 1,800 calorie per day diet? So how many do they consume in a year? So we start off with the idea that we have 1,800 capital C calories per day. And we want to know how many kilojoules per year that is. So the first thing we do is we convert 1 calorie, remember, is 4.184 kilojoules. The next thing we need to do is we'd say there are 365.25, because of leap year, days in 1 year. So now we have calories on top. It's going to cancel here. So we're left with kilojoules on the top. We have days, which is going to cancel with days right there, leaving us with years on the bottom. So at this point, we can take our calculator out, take 1,800, multiply it by 4.184, and then multiplying that by 365.25. When we do that, we end up getting a number like 2.75 million, or 2.75 times 10 to the sixth kilojoules of energy. It's a lot. Powering your devices. All of your electronic devices use electricity, whether it's a phone, a tablet, lights, air conditioning. Your car uses energy but not electricity. So if we want to look at where these devices actually get their energy, we need to look at how we get electricity. Now, how and where you get your electricity varies a lot depending on where you live. So if you were to look in here to Texas, you'd see that the distribution is primarily focused on coal and natural gas. Those make up the bulk of everything. If you were to come here to California, you'd see that it's primarily red, and then there's a significant portion of yellow. So it's mostly natural gas, and there's a lot of solar and wind and geothermal. So it depends really on where you live. There are some that are green, like we see here in North Carolina and South Carolina. They get a significant amount of their energy from nuclear. Illinois gets almost half its energy from nuclear. So because of that, it really depends on where you live as far as where you get your electricity from. But these are the primary culprits: coal, hydroelectric, natural gas, nuclear, solar, and wind. So, things to consider. Whenever you're considering things that you can ponder, is what are the products, pollutants produced by converting your source to electricity? So, when you burn coal, there are things like coal ash, and there's carbon dioxide, carbon monoxide, there's lots of things that are produced. Versus when you have something like solar, there's very little pollutants that are produced. So how much does it cost? Even though coal produces a lot of pollutants, coal is by far the cheapest. So it requires the least amount of energy or cost, whereas something like solar is very expensive to start up. Can production be increased, stored, or decreased when demand for electricity changes? What if it's cloudy outside and you use primarily solar panels and it's been cloudy for a month? Um, do you still have the ability to produce electricity? And then the last one is, can we run out? If so, when? Are we going to be out of oil? Are we going to be out of natural gas? Are we going to start declining? Those are things to consider whenever you consider energy sources.